Okay, hello everyone and welcome to this video on a spec question from the Trig Preliminaries Test exemplar that's up on the SACE board website. We'll be going through it together. It's a 7-mark question consisting of 4 key sub-questions. So let's have a little look at what's asking. So from sine 2x, which we know is an identity on the formula sheet for Specialist Mathematics, we know that that is equal to 2 sine x cos x. And from this we observe that sine x cos x is obviously going to be sine 2x on 2, because of course you're just dividing by 2, so you cancel out the 2's, and you can see that sine x cos x is obviously going to be that value there. So what we need to do with part A is we need to prove that sine x cos x 2x equals sine 2 squared x on 2 squared. Okay, so in order to do this, what we need to do is we need to start off by rewriting out what we have here. We have sine x cos x multiplied by cos 2x. Okay, so we know from the identity that this sine x cos x here is going to be sine 2x on 2. So we can sub that in. Sine x cos x is going to be sine 2x, obviously to the power of 1. And in the denominator it's going to be on 2, and then of course we have cos 2x there. And again that just remains in the numerator because it's multiplied in the original expression. So now what we have is we have sine 2x cos 2x on 2, and if we look at what we need to prove, we need to have the denominator equal to 2 squared, which is 4. So in order to do this, what we actually do is we essentially double both the numerator and the denominator. We times both of them by 2. So we get 2 sine of 2x cos of 2x all on 4. And what we notice from this is that we have 2 lots of sine 2x cos 2x. If we have a look at our identity, sine 2x equals 2 sine x cos x here, we can see that we essentially have 2x there and 2x there, and we've got the 2 out in front. So we can actually rewrite the denominator based on this to be sine 4x. And again, that's because we have a 2x term and a cos 2x term there, so sine 2x and cos 2x multiplied by 2. So it fits this sort of format here, but it's for sine 4x. And we know from before that that's over 4. So we can hence set that equal to sine 2 squared x on, and then 2 squared. And there's our little proof. Okay, so it's quite straightforward. It's just a matter of actually identifying the fact that those values have been doubled and being able to work towards the end goal. The end goal is to obviously show that that equals that, but of course we were able to identify what we needed to do by considering what the denominator said. So it's always good to evaluate it and actually work out, well, how do I get closer to showing this expression from that? In this case it was just a matter of simply multiplying both the numerator and denominator by 2. So always think logically about how you can get closer and closer to that step. So B says if sine x, cos 2x, cos 4x equals sine 2 to the 3x on 2 to the 3, then what does sine cos x, cos x, cos 2x, cos 4x, cos 8x equal? And it's quite simple. Let's have a look at the pattern. So we have 2x here, and we have the highest power 2. We have 4x here, and the highest power 3. And then we have finding it for 8x. So as we can see, we're essentially doubling each time. And because of that, we can assume, again, that we would have sine 2 to the 4x on 2 to the 4 for that. And then what we have is we have 32. So if we have a look at this, we've got 2x, 4x, 8x. Obviously the next one would be 16x, which would obviously be sine 2 to the 5, based on the pattern that we're assuming. And then the last one would be cos 32x, so it would be 2 to the 6 for that one. So we'd have sine 2 to the 6x on 2 to the 6. I won't bother writing that one out because it's quite straightforward. But the last question asks, what is the generalization of the results in parts A and B? And the generalization is actually pretty easy. You just need to identify what's going on in terms of powers of 2. So, when we're looking at powers of 2, there are a few things that we can begin to notice here. The first thing we notice is that our expressions, as you can see them here, obviously involve 2 to the power of something. For example, that's 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. So, what we know is that if we have, and I'll write it up here, I'll probably just clear some space. If we have sine x, and then obviously cos x, and then cos 2x, cos 4x, etc. until we get all the way up to cos to the nx, then we can write this as sine x, lots of cos to the 2 lots of 0x, because obviously 2 to the 0 is going to just be 1. Anything raised to the power of 0 is 1. Lots of cos to the 2 to the 1x, which is just cos 2x, and then cos to the power of 2, cos 2 to the power of 2, x, etc., until we get up to cos 2n to the x. Then we can rewrite this expression as, and we know it's going to be sine of, and then we're going to have 2 to the n, and of course let's evaluate the situation here. So we have 2 squared here, 4 is 2 squared, and we're getting 2 to the 3 in here, so it's going to be to the n plus 1, isn't it? So we're going to get 2 to the n plus 1x on, and obviously it's just going to be 2 to the n plus 1 as well in the denominator as a general form. So the way we were able to do that is just by looking at powers of 2. Look for a pattern. Here it's obviously doubling, and we just look at the exponents, how they fit in. So I hope this video was helpful in explaining this spec question. Let me know any issues you have in the comments below. Thank you for watching, and that's pretty much it.